Okay, so today we are going to solve some problems from Chapter 9, Chemical Reactions. And let's get started with types of chemical reactions. And I've selected 9.3, which basically has several reaction equations given and wants us to categorize them as being either combination reactions, decomposition reactions, displacement exchange, or combustion reactions. So going through section 9.1, where these reactions have been defined and explained, let's see if we can categorize them as one or the other. Okay, so looking at A, equation is 3 copper 2 sulfate plus 2 aluminum produces aluminum sulfate and 3 copper. Now in this reaction, we are starting out with an ionic compound reacting with an element, making a new ionic compound, which then kicks out the element from the cation of the first compound. So in this case, there has been an exchange, a single exchange, a single displacement where aluminum has displaced copper in the compound to make aluminum sulfate. So this reaction will be classified as displacement reaction. B, potassium carbonate makes potassium oxide plus CO2. Obviously, this reaction, one compound has been broken up into 2 smaller pieces, and therefore this compound is a decomposition reaction. This reaction is a decomposition reaction. Looking at the next one, 2 silver nitrate plus potassium sulfate gives us silver sulfate plus potassium nitrate, 2 potassium nitrates for this reaction. Now this reaction is an exchange reaction where both the compounds that we are starting with are exchanging their positions, making new compounds. So in the products, then silver, the cation of the first, is making a new compound with the anion of the second, and the cation of the second is making a new ionic compound with the anion of the first. So it's an exchange reaction. Next one, 2 phosphorus plus 3 hydrogens making 2 PH3. Now in this case, we are taking smaller units, putting them together to make one bigger unit, and therefore this reaction is a combination reaction. Sometimes combination reactions are also called synthesis reactions because you're synthesizing something bigger, but that's a combination reaction. So the first is displacement, then decomposition, exchange, and then combination. Just FYI, what would a combustion reaction look like? Yes, a combustion reaction is where you start out with compounds that are made up of carbon, hydrogen, and maybe also oxygen, such as C8H16, and when you heat them, they make carbon dioxide and water. Please note this equation that I have written right now is not a balanced equation. Hold on, I did make a mistake. When a combustion reaction takes place, the compound that is made up of C and H and also maybe oxygen does react with molecular oxygen in the air. There's a burning going on. Burning always involves reaction, a chemical reaction with oxygen gas in the air. So we do need that as a reactant, and the products will always be carbon dioxide and water. As I was saying earlier, I have not balanced this equation, so the moles, the number of atoms do not balance out on both sides of the equation. But the reaction will always, combustion reaction will always look like this, where a compound made up of CH and or oxygen combines with oxygen gas in the air, making carbon dioxide and water. Okay, let's move on to redox reactions. Now it is important to remember what reduction and oxidation are in terms of, okay, I need to get rid of this screen. Let's try that again. Okay, sorry about that. So in the redox processes, we need to know what's going on electronically speaking when a reduction or an oxidation process takes place. So it helps to remember that a reduction process involves gain of electrons when electrons are gained or are added on, and an oxidation process, I can't spell today, something is obviously not okay. Oxidation process is when electrons are lost in a process. So that substance, whichever one loses electrons, is said to be oxidized. Okay, so let's look at this problem 9.11, which says determine the oxidation state of each of the following. So in this case, as far as cations are concerned, oxidation state of metals equals the number of electrons that they lost, and oxidation state of nonmetals equals the number of electrons they gained if they made an anion. Please also remember, as it specifies in section 9.2, oxidation state of elements, whether they are atomic or molecular elements, is always 0. There is no oxidation or reduction going on there, and so we'll go with that. So let's look at A. They're asking for oxidation of barium in barium 2+. So since this is a cation, barium 2+ is a cation, the charge is 2+, the oxidation state of barium therefore is +2. B, they need us to figure out oxidation state of sulfur in sulfur trioxide. So in this problem, what we'll have to do is we'll have to pretend as if it were an ionic compound. Now sulfur is less electronegative than oxygen. Because oxygen has a higher electronegativity, oxygen will have a negative oxidation state and sulfur should have a positive oxidation state because of that difference. So with that in mind, if we pretend that this is an ionic compound, what is the total negative charge on the 3 oxygens? So keep in mind, each oxygen would have a charge of -2, and therefore 3 of those will be -6, and therefore sulfur will be +6. So even though it's a molecular compound, it is not an ionic compound. In order to figure out the oxidation of sulfur, we are doing this analysis, and based upon that, the oxidation of sulfur is +6. C, fluorine in F2. As I said before, oxidation states of elements is always 0, whether those elements are atomic elements or molecular elements. Now F2 is not a compound, it's a molecule, but it is a molecule of the fluorine element, and because of that the oxidation state of fluorine is going to be 0. Okay, D, phosphorus in the ion PO4 3-. Okay, now for this we again have to analyze and see first of all, we have to establish which atom is more electronegative, phosphorus or oxygen. Agreed, oxygen is more electronegative than phosphorus, and then we have to then also keep in mind that there's an overall charge of 3- on phosphate. So if I break this up, phosphorus separate from the 4 oxygens, the overall charge on the entire piece is 3-. Now remember that each oxygen has to have a charge of 3-, excuse me, I misspoke. Each oxygen has to have a charge of 2-. So if we do that, the total negative within the ion is 8-. But there's an overall charge of 3-. In other words, after the plus and minus cancel each other out, 3 minuses are left over. So which means therefore that phosphorus must be 5+, because 5+ and 8- together leave or a residual charge of 3-. So in this case, the oxidation state of phosphorus is +5. Okay. Let's look at 9.13, same idea, but this time there is a combination, well, they're all ionic compounds, and once again, the idea is not going to change though. So let's get started with Cr2O3. So let's think about it. Cr, O, O, and O. If each O is 2 minus, then the total negative is 6 minus, total plus has to be 6 plus, and therefore each chromium is 3 plus, which means that the oxidation state of chromium in this compound is plus 3. B is again exactly the same. The question is CrO2. I really like to break it up. Once again, 2 minus, 2 minus, total 4 minus. So this must be 4 plus, and there's only one chromium there. So the oxidation state of chromium here is plus 4. Now let's do something. If you follow the same logic, exactly the same way as before for C, which is CrO3, I hope you will realize that the oxidation state of chromium in this case is plus 6. Okay, let's do something a little bit different. For example, D, which given formula is Na2CrO4. Now this is an ionic compound. If it's an ionic compound, what is the charge on the chromium containing ion? In this case, that's the anion, chromate. So sodium, please remember, has to have plus 1. There are 2 sodiums, therefore the chromate is 2 minus. Now we need to do what we did in the previous problem, realizing that there is a residual charge of 2 minus, so CrO, and O. Residual charge, of course, is 2 minus. Let's not forget that. Each oxide is 2 minus, 2 minus, 2 minus. That gives us 8 minus, and which means that chromium in chromate has to be plus 6. In other words, the oxidation state of chromium in sodium chromate is plus 6. Okay, so if you do the same analysis for all the others, I'm going to do a couple more in this. Once again, barium chromate, same anion actually as the previous example, and therefore chromium is going to be plus 6 in that as well. Excuse me. F, barium BaCr2O7. Now this is barium dichromate. The idea doesn't change at all, and if you work through this problem like we did in part D, you will come to the conclusion that chromium in this is also plus 6. I just want to do a different one before in this problem before I move on to the next problem. So that would be H. H is CrF5. This is not an this is a compound where 5 fluorine atoms are connected to one chromium. So which is more electronegative, chromium or fluorine? Yes, you're right, fluorine is more electronegative. So if there are 5 fluorines, each fluorine brings in -1 because it is more electronegative, which means chromium must be plus 5. So this is an example where chromium's oxidation state is plus 5. Okay, let's move on to the next problem. What is the oxidation state of each of the element in each of the following substances? So exact same idea. Nothing has changed here. The process will also be the same. So if you look at PF3, phosphorus is plus 3 because it's less electronegative, and fluorine being more electronegative, each fluorine has an oxidation state of -1. B is an ionic compound, sodium hydroxide, and since it's ionic, sodium has to be plus 1. Oxygen in hydroxide has an oxidation state of -2, and hydrogen in hydroxide has an oxidation state of plus 1. Sodium sulfate, again sodium, each sodium has an oxidation state of plus 1. Sulfur has an oxidation state of plus 6 because sulfur is less electronegative than oxygen, and oxygen in this compound, each oxygen in this compound has an oxidation state of minus 2. Carbonate anion this time. Carbon in this anion has an oxidation state of plus 4, and each oxygen in this has an oxidation state of minus 2, so that there's a residual charge of minus 2 for the whole anion carbonate. But the process of determining oxidation states in each element doesn't change, it stays the same. Okay. Now we need to classify each of the following reactions as being redox reactions or non-redox reactions. In other words, are the oxidation states of substances changing when the reaction is happening or not changing? If those are changing, then the reaction is a redox reaction, otherwise it's not. So in the first one, 2 copper plus oxygen produces 2 copper 2 oxide. Now, what is the oxidation state of copper in the reactant? Yes, it's 0. What's the oxidation state of oxygen in the reactants? Is also 0 because that is an element. But what is the oxidation state of copper in the product? Yes, it's 2 plus, and the oxidation state of oxygen is 2 minus. So please note that copper, when it went from 0 to 2 plus oxidation state, lost electrons. Oxygen, on the other hand, gained electrons. In other words, one substance was reduced while the other one was oxidized. So this reaction is definitely a redox reaction. Now let's look at second equation, which is potassium oxide plus water, H2O, gives 2 potassium hydroxides. Again, same analysis. What's the oxidation state of potassium in potassium oxide? Yes, it's plus 1, each one. Oxygen is minus 2. What about hydrogen oxidation state and oxygen in water? Hydrogen is plus 1, each hydrogen is plus 1, and oxygen is minus 2. When you look at potassium hydroxide, have those changed? No, the potassium is still plus 1, oxygens are still minus 2, and hydrogen is still plus 1. So you notice that none of the oxidation states have changed in this reaction. So this reaction is a non-redox reaction. C, 2KClO3 produces 2 KCl plus 3 oxygen. Now when you do this, when you look at this equation and do this exact same analysis, you will notice that the potassium's oxidation state is not changing. But chlorine in the reactant is a plus 5. Chlorine in the product is minus 1. Oxygen in the reactant is minus 2, but oxygen in the product is 0. So one is getting reduced. In this case, when you're going from plus 5 to minus 1, there was electrons gained, reduction, whereas another one is getting oxidized because it's going from a negative oxidation state to a 0, meaning it lost electrons. So this is definitely a redox reaction. D, methane CH4 plus 2-ox, this is a combustion reaction. Combustion reactions are always oxidation, reduction, oxidation processes because there is oxygen involved. But if you do the analysis, you'll come to the same conclusion. Hydrogen in CH4, if you remember the relative electronegativities, carbon is actually less electronegative slightly than hydrogen is. So, I'm sorry. Yes, so there is an overall change. Once again, same analysis. There's an overall change in the oxidation states of the elements, all the elements in this case, and therefore this is a redox process as well. Okay, let's look at 21. Classify the following reactions as being redox and non-redox, and also classify them as being combination, displacement exchange, or combustion. Okay, so zinc plus copper 2 nitrate makes zinc nitrate plus copper. Now doing the same analysis, zinc is 0 in oxidation state of zinc is 0 in the reactants, but it's +2 in the products. Copper is +2 in the reactants but 0 in the products, which definitely suggests that this is definitely a redox process. But besides being a redox process, zinc is displacing copper in copper nitrate to make zinc nitrate and kicking out copper as elemental copper. So this is also a displacement reaction. Let's look at the next one. Methane, same thing, oxygen making CO2 plus 2H2O. Now this reaction is a redox process. There is oxygen being reduced and hydrogens being oxidized in the process, and at the same time, because a carbon hydrogen containing compound is reacting with gaseous oxygen to make carbon dioxide and water, it is also a combustion reaction. 2CuO makes 2Cu plus O2. Copper in this case is going from +2 oxidation state to 0, so it is being reduced, it's gaining electrons. Oxygen is going from -2 to 0, it's being oxidized. In other words, it is losing electrons. So this is a redox reaction, and as far as the other classifications are concerned, a big unit is being broken down into smaller pieces, therefore it is also a decomposition reaction. D, sodium chloride plus silver nitrate making silver chloride and sodium nitrate. Now if you notice, look at the charges of everything and the oxidation states of all the elements in this reaction, you will notice that there are no changes. Silver stays +1, starts +1, stays +1. Sodium starts +1, stays +1. Nitrogen and oxygen and chlorine, chlorine's oxidation stays -1. Oxygen's stays -2, and nitrogen stays +5. None of them are changing. Therefore, this is not a redox reaction. It is a non-redox process. But at the same time, it is also an exchange reaction because the cations and anions are exchanging company. They are making new compounds with each other, and therefore falls in the category of exchange reactions. Okay, so looking at the next problem now we're talking about terminologies associated with redox and non-redox chemical processes. So 23 says identify the substances that is oxidized and the substances that are reduced in each of these redox reactions. So let's take a look. Nitrogen plus 3H2 makes 2 ammonia. What is the oxidation state of nitrogen in N2? Yes, it's 0 because it is an element. What about hydrogen in H2? Also 0 because it's an element. Now, what about in ammonia? Which is more electronegative, nitrogen or hydrogen? Yes, it's nitrogen is more electronegative than hydrogen. So hydrogens are +1, nitrogen is -3. So in this case, which element was reduced? Which element gained electrons? Yes, nitrogen was reduced and hydrogen was oxidized in this process. Same analysis for the next one as well. Chlorine plus 2 Ki makes 2 KCl plus iodine. Oxidation state of chlorine in Cl2 is 0, potassium is +1, iodide is -1, potassium in product still stays +1, no change, but chlorine is now -1, iodine is 0. So chlorine went from 0 to -1. In other words, it was reduced. Electrons were gained. Iodine, on the other hand, went from -1 to 0 by losing electrons, and therefore it was oxidized. Spe2O3 plus 3 Fe makes 2 Spe plus 3 FeO. Oxidation states to start out with for the stilbene. So, oh sorry, is that stilbene or antimony? Yes, sorry, it's antimony, not stilbene. I apologize. So the oxidation state for antimony in the reactant. So if you think about it and analyze oxygens being -2, which means each antimony will be +3. Iron in the reactants is 0, antimony in the product is 0, and iron in the product is, if oxygen is -2, iron will be +2. So in this case, antimony went from +3 to 0. And the only way to do that is by gaining electrons. In other words, antimony was reduced in this reaction, whereas iron went from 0 to +2 by losing electrons. In other words, it was oxidized. Last one, 3-sulfurous acid plus 2 nitric acid makes 2NO plus H2O plus 3 sulfuric acid. Okay, so in this reaction, once again, I would encourage you to do exactly the same kind of process, go through the same process. But if you note that sulfurous acid was oxidized because there was a net increase in its oxygen content, and if you work out the oxidation states, that's the conclusion you would come up with as well. And nitric acid, on the other hand, in this case, was reduced. Okay. Let's move on to the, next one, 25. Identify which substances in the is the oxidizing agent and which is reducing agent in each of the reactions as before in 23. Okay, so here we have to remember that an oxidizing agent actually gets reduced itself, and the reducing agent gets oxidized itself when the reaction is taking place. So if you look at the first reaction, we talked about it before, N2 plus 3H2 making 2 ammonia, which was getting reduced. So nitrogen is 0, hydrogen is 0, nitrogen now is -3, hydrogen is +1. So which substance is getting reduced in this process, meaning it's gaining electrons? Yes, nitrogen is gaining electrons. It is being reduced. That means that nitrogen, nitrogen is the oxidizing agent. Isn't that what the question is asking? I'm just going to confirm that. Oxidizing agent, yes. So nitrogen is then the oxidizing agent. And if nitrogen is the oxidizing agent, then hydrogen is therefore the reducing agent, because it is itself getting oxidized. So once again, I'm not going to go through the whole analysis, but if you look at each of the same reactions as the question before, substance that is getting oxidized is the reducing agent, and the substance that is being reduced is the oxidizing agent. So if we look at the same question equation number B, we should come to the conclusion that chlorine is the oxidizing agent, and iodide, actually, iodine, potassium is a counter ion with iodide, but it's actually iodide which is doing the reducing. So iodide is therefore the reducing agent. C, antimony oxide will have to be the oxidizing agent, because antimony because antimony is the one that got reduced. Antimony cation was the one that was reduced, and at the same time metallic iron will be the reducing agent, because that's the one that was oxidized in the process. D, since sulfurous acid was, since nitric acid was reduced, nitric acid is the oxidizing agent. And since sulfurous acid was oxidized, sulfurous acid is the reducing agent. So we need to remember that the substance that is reduced during a reaction is the oxidizing agent, and the substance that is oxidized in a reaction, that's the reducing agent. Okay, let's talk about exothermic and endothermic reactions. Exothermic reactions are those reactions that in the end release energy. There is a net creation of energy in exothermic processes. In other words, the products have a lower amount of net energy compared to the reactants that we started with. Endothermic is just the opposite, where there is a net consumption of energy. Energy is overall absorbed through the process, which means basically that the products have a net higher energy compared to the energy of the reactants. So let's analyze the question number 35, which basically asks us to categorize these reactions being endothermic or exothermic. Now, again, a very quick hint: if heat was produced, it's exothermic. If heat was used, it's endothermic. So if you look at the first reaction, C2H4 plus 3 oxygen gives 2 CO2 plus 2 H2O plus heat. Heat was in the product side of the equation. It was made as a result of this reaction. So this reaction is therefore exothermic. Energy was released. B, nitrogen plus 2 O2 plus heat makes. Now this time heat was a reactant. It was consumed. It was used up. And therefore, this is endothermic process. C, 2H2O plus heat gives us 2H2 plus O2. Guess which reaction, which kind of a reaction this would be? Heat was a reactant. Exactly. This is endothermic because heat was consumed. D, 2KClO3 produces 2KCl plus 3O2 plus heat. Heat is a product. It was made, it was released, and hence that's exothermic reaction. Okay. 39. Sketch an energy diagram representing an exothermic reaction and then label the following. So when you're drawing an energy diagram, the x-axis is, let me try that again. When you're drawing an energy level diagram, the x-axis, the y-axis has the energy of the system, the whole system. The x-axis is the reaction progress. As the reaction is progressing, starting with time 0 to how much ever time it takes. So when we start the reaction, we start with just the reactants. So let's say this is the energy of the reactants. And if it's an question 39 was asking for exothermic. This is for exothermic. I need to make a note. So question 39 is asking for exothermic reaction. So in exothermic reactions, energy is released, it's produced, which means that the energy of the reactants is higher than the energy of the products. All reactions have to go through an initial hump. In other words, there will always be a barrier, an energy gain, and then a loss of energy to give the products. But for an exothermic reaction, what is important to note is that the average energy of reactants, so this is the average energy of reactants. I don't have enough room to write this. That's the average energy of reactants. This is what we are starting with. This is the average energy of the products. So for every exothermic reactions, the average energy of the products will always be lower than the energy of the reactants. There is a net release in energy. The amount of energy that is released once the reaction is done is this much. This is the energy that is created, it's released, it's produced. The question is, of course, also asking us to label activation energy. Now, activation energy is defined as the energy needed to cross that bump, that hump in all energy diagrams. So when initially there will always be an absorption of energy till we reach this peak in the diagram, this peak. So this energy that is needed to reach the peak in that energy diagram is the activation energy, also known as EA, to symbolize activation energy. So that's the amount of energy that will initially have to be absorbed, and then all the others will be released so that there is a net release of energy for exothermic reactions. So that's the energy liberated when the reaction takes place. Now, I thought I'll draw for both exothermic and endothermic reactions. Endothermic reaction, which is question number 40, same thing, we plot energy on the y-axis and reaction coordinate or the reaction progress on the x-axis. We always start with the reactants. That's the reactant energy, and then the product. Now, in endothermic reactions, there's a net consumption of energy. In other words, the energy of the products will always be higher than the energy of the reactants. As before, there will always be an energy bump, and then there. I'm not a very good drawer, as you've probably already figured out by now, but I'm trying my best. So here is the energy of the reactants, and I guess I'm not even a good writer today. And this is the energy of the products. The activation energy this time is, yes, the peak and then the reactants. So this is the activation energy, and the energy that was actually consumed in endothermic reactions. That's the energy, I don't have space. That's the energy used up or consumed in the endothermic process. That's the energy that was absorbed. Okay. Factors influencing chemical reaction rates. Let's get started with that. Question number 47. Draw energy diagram graph for an exothermic reaction where no catalyst is present. And then draw, okay, so we are asked to draw an energy diagram. So energy, y-axis, let's try that again, better, can do, okay. And reaction coordinate or reaction progress on the x-axis. And it says to draw one for exothermic reaction, in other words, reactant energy will be higher than that of the product. So this is without a catalyst, just a normal exothermic energy diagram. Then they say draw an energy diagram graph for the same reaction when a catalyst is used. When a catalyst is used, the reaction of the, when a catalyst is used, the energy of the reactants and the energy of the products does not change. Those remain the same. The only thing that changes when a catalyst is used is the activation energy. When a catalyst is used, catalyst lowers or decreases the activation energy of a reaction and therefore makes the reaction go faster. So what a catalyst does is lowers the hump needed to be crossed in order to go from reactants to products. That's all it does. Without a catalyst, if you notice, this is the activation energy without a catalyst, and this is the activation energy. This is the activation energy with a catalyst. So the only thing a catalyst does, one more time, is lowers the activation energy of a system and therefore makes the reaction go faster, because more number of molecules will now have enough energy that will allow them to transform from the reactants to the products. Question number 57. This has to do with chemical equilibrium. Okay. Let's consider the following equilibrium system: nitrogen gas plus oxygen gas makes 2NO gas. First part says, write the chemical equation for the forward reaction. Forward reaction implies a reaction that's written as going from left to right. In other words, forward reaction in this case is simply N2 gas plus oxygen gas going to make 2NO gas. Reverse reaction for equilibrium system is the reaction that goes from right to left, product to reactant. So in this case, that would have to be 2NO gas going to N2 gas plus oxygen gas. So forward is in that direction, left to right. Reverse is in this direction. Oops, all the blues are getting mixed up. So one more time. Forward reaction goes from left to right. Reverse reaction, right to left. Okay. Question number 67, also equilibrium constants this time. Write equilibrium constant expressions for the following reactions. So, okay, what did I do here? Nope, that's not what I wanted to do. Okay, so, there we go. We are back on track. Yay. Okay, let's try that again. 67, right? Equilibrium constant expressions for the following reactions. Okay, so equation A says N2O4 gas, equilibrium 2NO2 gas. When you're writing equilibrium constants, the K equilibrium is equal to, K equilibrium equals concentration of the products raised to the power of the coefficient divided by concentrations of the reactants raised to the power of their coefficients. The other thing that's very important to remember when you're writing equilibrium constant equations is Only gases and solutions make it into the equilibrium constant equation. Solids and liquids, pure solids and pure liquids, do not make it into this equation. So if you look at this, both reactants and products are gases, so they would both apply. Therefore, concentration of the product raised to its coefficient divided by concentration of the reactant raised to its coefficient, which in this case is 1. That is it. Okay. B, COCl2 gas makes CO gas plus Cl2 gas. So K equilibrium, I am having trouble writing today, absolutely. Okay, one more time. K equilibrium, so product concentration and only gases and solutions, not pure solids and pure liquids. Both of them have coefficients of 1 divided by concentration of reactant, also raised to its coefficient, which is 1. Let's try one more. Let's try, okay, C is good. CS2 gas plus 4 hydrogen gas makes CH4 gas plus 2 H2S gas. Once again, following the same idea, concentration of methane times concentration of hydrogen sulfide raised to 2, because this time the coefficient is 2, divided by concentration of carbon disulfide times concentration of hydrogen gas raised to 4, because its coefficient is 4 in the balanced equation. If you look at question number 69, it's exactly the same as the one before. The difference is that now some of the substances are either pure liquids or pure solids. Those substances do not make it into the equilibrium constant equation. So if you look at A, it says H2SO4 liquid equilibrates to SO3 gas plus H2O liquid. So when you're writing the equilibrium constant for this equation, this reaction, sulfuric acid will not make it into the equilibrium constant equation because it's a pure liquid, and nor will water for the same reason. So the only substance that makes it into the equilibrium constant equation is sulfur trioxide. So equilibrium constant in this case will be equal to the concentration of sulfur trioxide. If you look at, let's try a couple more. 2 silver solid plus Cl2 gas gives us, or equilibrium 2 AgCl solid. Now in this case, once again, silver solid will not make it into the equation, neither will silver chloride, because they are both pure solids. So when you write the equation, it will be equal to, now there is nothing in the product that makes it into the equilibrium constant equation. So there will be nothing on the numerator, in other words 1, and the denominator is just Cl2 concentration. C, barium chloride aqueous plus sodium sulfate aqueous produces 2 sodium chloride aqueous and barium sulfate aqueous. Now here all the substances in this equation are solutions, so they will all make it into the equilibrium constant equation. So sodium chloride concentration raised to 2 times barium sulfate concentration divided by barium chloride concentration times sodium sulfate concentration. If you look at the last one, the equation is 2 sodium oxide solid produces 4 sodium liquid plus oxygen gas. So please note, pure solids do not make it into the equation, pure liquids do not make it into the equation. So K equilibrium in this case is only That's it. So that's equilibrium, writing equations for equilibrium constants. How about calculating them? So let's look at an example of a reaction. The reaction in this case is N2O4 gas, equilibrium to 2NO2 gas. And we are told in this case that the concentration of N2O4 is 0.213, and the concentration of NO2 is 0.0032. So what is the K equilibrium equation, first of all, in this case? Yes, it will be NO2 concentration squared divided by concentration of N2O4. If you plug in the numbers, 0.0032 square divided by 0.213. Okay, so let's calculate this out. 32 times 0.0032 divided by 0.213, and I get the answer as, and significant figures should be in two significant figures, so I get 4.8 times 10 raised to minus 5 as the equilibrium constant for this question. Okay. 73. In this case, they've given us equations and the K equilibrium values, and they're asking us to predict whether the reactions that are said will have relative amounts of reactants or products depending on the K equilibrium value. Now, to answer this question, I would refer you to page 259, table 9.2. And using this table, you can answer this question very, very easily. So, for example, part A of this question has a K equilibrium at 25 degrees Celsius of 2.0 times 10 raised to 9. According to the table on table 9.2, excuse me, according to the table 9.2 on page 259, if the K equilibriums are large, so I would say between 10 raised to 3 and 10 raised to 10, then there is more products than the reactants. So all you have to therefore do is there'll be more products than the reactants based upon that table. B, K equilibrium is given as 3.2 times 10 raised to minus 34. So once again, going back to the table, when the K equilibriums are very small, less than 10 raised to 30 or below that, then essentially the reaction equilibrium is all towards the reactants, and there's hardly any products in here. C, K equilibrium given is that's at 460 degrees Celsius. That's a pretty high temperature. Okay, it's 85.0. Going back to the table, if you follow the table, you would predict that this reaction will have significant amounts of both reactants and products, because the equilibrium constant is sort of in the middle. There'll be almost equal amounts of both reactants and products. So, and D, equilibrium constant given is, I lost my questions. Just one second. Yes, K equilibrium given is 0.046. Once again, following the table, we would predict that there is pretty much the same, both reactants and products. So for this question or question of this kind, I would recommend that you use the table, once again, table 9.2 on page 259 in the current textbook. Okay. Equilibrium constants, question number 75. Write a balanced equation given the K equilibrium constant equation. So the equilibrium constant equation given in this problem is KEQ is equal to N2 concentration square, H2O raised to 6, ammonia concentration raised to 4, times oxygen concentration raised to 3. So if this is the equilibrium constant equation given to us, how do we write the reaction equation based on this information? So remember that these are the products. On the numerator are the products, denominator are the reactants, and all the powers, all the exponents are the coefficients that go with each of those substances. So using that, I can easily say the equation is 4 NH3 plus 3 O2 produces 2 N2 plus 6 H2O. You can of course confirm that by balancing this equation, making sure all the atoms balance out to confirm that this is true. Oh, one thing I did make a mistake on, it's an equilibrium process. So you must show arrows going, reaction arrows going both in the forward as well as reverse directions. What about states? Since pure solids and pure liquids do not make it into equilibrium constant equations, I would assume that all of these are gases. So gas, 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 and gas. Okay. Let's talk about Le Chatelier's principle. Le Chatelier's principle, and I may be pronouncing their name wrong, but this principle basically says that if you have an equilibrium system and you disturb the equilibrium by changing factors in one direction, then the equilibrium shifts to balance to counteract that change. And therefore, there'll either be more products made, or it'll shift to the reactant side and less products, so on and so forth. So if you look at problem 83, and the reaction equation given for this problem is 2 chlorine gas plus 2 H2O gas, equilibrium 4 HCl gas plus O2 gas. Okay, so determine in which direction the equilibrium will shift for this reaction if the following changes are made. So in A, if we increase chlorine concentration. If chlorine concentration increases, in other words, we are increasing one of the reactants amount, the equilibrium will automatically shift in the direction of the products. So we will have, therefore, more of the products. It will shift to the right. Okay, B, if we increase the oxygen concentration. Oxygen now is in the product, so if you increase the oxygen concentration, the reaction equilibrium will shift towards the reactants instead to counterbalance that change in the equilibrium, and yes, and some of that product will get used up. C, we are now decreasing water concentration. Water is once again in the reactants, so and we are decreasing it. If we are going to decrease it, the reaction will shift more to the reactants in order to create it more so that that balance can be achieved again. D, decreasing HCl concentration. HCl is in the products. If you decrease its concentration, the equilibrium will shift towards the right in order to make more of it and once again to balance that out. Okay. 91. So problem 91 indicate whether or not product formation increases or with increasing temperature in each of the following equilibrium systems or decreases. So once again, it's Le Chatelier's principle. If the reaction is exothermic, in other words, heat is produced, decreasing the temperature, if you decrease the temperature, take away some of the heat, then that will affect the reaction to to counterbalance that change in the reaction. So if you look at equation number, the first equation A, which says nitrogen gas plus 2 oxygen gas plus heat. So this is an endothermic process and makes 2 NO2 gas. And now if we decrease, are we increasing the temperature or decreasing the temperature? Just a second. Indicate whether or not product formation will increase or with increasing temperature of the, okay, so we are increasing, we are increasing, raising the temperature this time. So if you're going to raise the temperature, in other words, you're going to raise the amount of heat going into the system, and if you're going to raise the amount of heat going in the system, the equilibrium will shift in this direction, so then there will be more of the product. In the second case, heat is again a reactant, so it's also an endothermic process. 6H2O gas making 4 ammonia gas plus 3 oxygen gas. So same thing here as well. Since heat is a reactant, it's an endothermic process, and if we increase the temperature, we are increasing the amount of heat. Therefore, the reaction equilibrium will once again push in the direction of the products and give us more products. Oh, that was B. I'm sorry. That was B. C, C2H4 gas plus 3 oxygen gas makes 2 CO2 gas and 2 H2O gas plus heat. This is an exothermic process. If it's an exothermic process, heat is one of the products. Now if you increase the temperature, you increase the amount of heat, and therefore the reaction has no choice but to go in the reverse direction more, and therefore there will be a decrease in the amount of products made. Last, 2 KClO3 solid plus heat, 2 KCl plus 3 oxygen gases. Now what do you think here it will be? Remember, heat is in the reactant, and by increasing the temperature, we are increasing the heat. If you're increasing the heat, the reaction shifts towards the opposite direction in order to counteract that change, and therefore there is more of the product being made in this case.